NASA will soon be returning astronauts to the moon, this time to stay. Because of this, the search for and study of water ice on the lunar surface is of critical importance. When it comes to volatiles and water ice, one of the most interesting areas is the South Pole. We'll need maps for both rover and human explorers. Machine learning offers the potential of enhanced resolution images of this region, providing vital information for future rover and human traverse mission planning. But there's an important catch. We also need good evaluation metrics for the results to be trusted. To tackle this problem, I'm delighted to introduce the Moon for Good 3 team, Upscaling Lunar Resources.
Hello, everyone, and welcome to the Upscaling Lunar Resources team presentation. My name is José Ignacio Delgado, and I'm here with my teammate Paula Harder to introduce ANUBIS, the solution that we have been developing during the past 8 weeks here at FDL. But before getting into the solution, I would like to talk a little bit about the context, even though we saw an amazing video just now. So even though Mars had been on the picture for quite a long time, we are going back to the moon. Humanity should return to the moon, and this time we want to stay there. So here at FDL, we want to provide some help to achieve this goal, as we can see here. And there are plenty of missions that are going to be happening on the lunar surface in the upcoming years with many objectives, such as scientific research to, for example, understand better the origin of our planet, lunar resources detection and extraction, where we process ice, for example, to be able to keep astronauts on the lunar surface for a longer time, and also solar system exploration, as we will be using the moon as a stepping stone to go to other places in a way more efficient way than what we are doing right now. Okay, so in order to plan all these missions, one key element are like the lunar surface images, in order to understand what's on the lunar surface and which places are most interesting for us. And the greatest database that we have available right now is the one provided by the NASA's Lunar Reconnaissance Orbiter mission. So this satellite has been orbiting the moon for 12 years now, and it's providing a lot of data, such as this image that you can see here. Images from the lunar surface, so now the whole moon is mapped actually in this database. But there is a little problem with these images. So the resolution of the images is depending on the altitude of the satellite when the image is taken, and also the lighting conditions at this moment. So let's take a look at the southern hemisphere. So we can see here how, for example, if we look at images with 1 meter per pixel resolution, there are plenty of them. There are the orange dots here. But if we look for images that have a higher resolution, let's say 0.5 meter per pixel, there are not that many, especially on the core of the South Pole. That is the target for the upcoming mission that I mentioned just a minute ago. So this is the problem that we want to help with. This is what our solution was focusing on. And here is an example of what does it look like at 1 meter per pixel image. So this is the Apollo 16 landing site. And we can see here how the features of the lunar surface are not really clear. But if we go to 0.5 meter per pixel, we can see clearly where the craters are and where like the obstacles for example, potential navigation on the lunar surface can be. So let's say that we want to, again, to do some traverse planning for a rover in the lunar surface. If we are working with 1 meter per pixel resolution, it's going to be a hard task because we are not sure where the obstacles are. But if we transition to this 0.5 meter per pixel resolution, we can see clear where they are, and then we can navigate safely in the lunar surface. So this is the problem that we tackle, and therefore we go to our actual application, ANUBIS. ANUBIS stands for an adversarial network for uncertainty-based image super resolution. And again, it's the one that we have been working on for the past week. And now I'm going to let my teammate Paula go through the solution and also like the results that we have gotten so far.
Thanks, Jose. Welcome from my side. So I'm going to introduce ANUBIS now. The core of ANUBIS is a residual neural network, the generator you see here. It gets a low-resolution image as an input and generates a high-resolution image. But to train this network, we need pairs of high-res and low-res images. And we get them by looking at sites where we actually have high-res images and then downsample them to get their exactly matching low-resolution counterparts. When we train the network, the generator, we introduce the discriminator, and they play an adversarial game against each other. The discriminator tries to tell the real low-res and the real high-res and the generated high-res apart, whereas the generator tries to fool the discriminator. This way, the output here gets better and better and closer to the real high-res. So what we get is a real high-resolution output image from the generator. We not only produce this high-resolution image, we also produce an uncertainty map along with it, using a deep ensemble method. It shows us in which areas of the image we fully trust our prediction and in which areas we might look into more detail or we want to stay away of. You can see here dark green means full trust, whereas a red bit would mean we are not very certain in this area, just here in the upper corner, and yellow is something in between. We applied our model to the Shackleton-Ridge area, an area of interest for the Artemis program, for example. It's an area very close to the actual pole, but there are no high-resolution images there. So we looked at this 1 meter per pixel low-resolution image, and it's hard to see detailed features. For example, in the zoom in, you can see here a big crater, probably a smaller one, but apart from that, it's very hard to see. Now we apply our model, and we can see how we get much better features. We can see 2 craters here and like a big footprint shape in the zoomed in area. We validate our model, and for that we need real low-res and high-res pairs. We found a site where we do have both. So this is a real low-res pair from the LOO database, a real low-res image. We apply our model, and now you can see clearly how much more details and features we get. This is the ANUBIS output. And then we compare it to the actual real high-res image, and we can see how close we get with our prediction. It's hard to tell them apart. To make sure to show that our solution can be used for applications, we applied some path planning. You can see here how in the low-res image, the path which is taken to avoid obstacles takes a detour because we're not sure if we can traverse this area here. Whereas in the generated high-res, we get a much more optimal path, which is very close to the actual high-res path. To sum up, ANUBIS enables us to enhance images from all over the moon. We targeted the South Pole now, but the model can be adapted to any parts of the moon. It increases the resolution of an image by a factor of 2. And with this, we are able to detect and map hazards which are currently unknown. We not only produce those super resolution images, we also give an uncertainty estimation along with them to make it feasible for safety critical applications. We hope that with our solution, we can contribute to future lunar missions. We can help humanity go back to the moon, establish a base there, and go beyond. Our team here already made it to the moon. That's me, Paula, Jose, who presented before me. We're the 2 researchers. Then you see our great team leads, Sida, Miguel, Ben, and Valentin. And we want to thank our team advisors, Freddie, Mo, Jari, and Chedi, for their great help. And also our sponsors, especially Luxembourg Space Agency. Without them, this challenge wouldn't have been possible. Now we want to thank you for watching.
Thank you so much, Lunar team. Really awesome work. I'm excited to hear what words Scott comes up with, because wow. But with that, I'm going to go ahead and turn it over to Bill and our panel.
All right. Thank you very much, Sarah, and thank you, team. You know, these images and the work you've done remind me of all those things you see in the movie, you know, when trying to solve the crime. They're looking at some low resolution image of a car in the distance, and somehow they're magically able to zoom in on this speckled image and read the license plate. But, you know, that's the movies, and this is the real deal. Joining Scott and I to talk about this work is Brian Day. Brian is Deputy Staff Scientist at NASA Ames, and he's part of the Solar System Exploration Research Virtual Institute, or SERVI there. So welcome, Brian. And Brian, let's start with you and ask you, from your perspective, what are the takeaways here, and how do you see this work contributing to future NASA missions?
Well, this is very exciting work. Right now, there is a concerted effort amongst NASA and its partners to characterize upcoming landing sites as well as potential traverse paths. And as has been mentioned, the gold standard is the LRO NAC data. And our ability to do analyses are constrained by the resolution of that data. This work here has the promise of really opening that up and giving us a much finer view. And so I am very much looking forward, as I know a number of other people are, to be able to take the output from this super resolution work and be able to feed it into our AI tools for doing crater detection, boulder detection, and be able to do these analyses. These will allow us to really make the bold moves to explore this very new and different terrain.
So, you know, the FDL program has done lunar resource work. You know, the metals mapping that were done as part of last year's program, and now these permanently shadowed regions and the image enhancement there. What would you say you'd like the teams to focus on next year? What's the next stage for this work going forward?
Is it to me?
Well, I was going to ask Brian. I've got another question for you, Scott.
Oh, this is Brian. I go to Brian. He's
one thing I'm very, very intrigued by. Of course, so one of the things that, of course, we're very intrigued by the NAC data that is then the new features that are going to be revealed. But the potential for this technology to be applied to other data sets is also really fascinating. One of the things I look forward to seeing is, for instance, seeing this applied to the lunar orbiter image recovery data, and being able to now look at temporal changes in the moon, on the surface of the moon. That really is exciting. And so this technology applied to the NAC data is wonderful, but it has applications that could go well beyond that.
Yeah, absolutely. Scott, I was going to ask you about the AI and the ML. You know, this is one of those areas where the AI tool does look like that black box. It looks like this magic thing that takes this low resolution image and turns it into this high resolution image. And of course, the team talked about the training sets and so forth. But how does that work, and how do we, you know, we trust these enhanced images?
You know, I can't help but think, Bill, I'm reminded of a few centuries ago, someone started thinking about physics and optics and curvature and material science, and those were glasses. And I think, you know, for Ben Franklin. So I think what you all are inventing here, I think is a very powerful, like, I wear glasses, we all wear glasses. I think as you think about exploring the heavens and we go out, our instruments need the same. And it has to do with physics. Because you can't backhaul, as Brian knows, you can't backhaul high-res images from Mars or from other you know, moons. So what you have to do is, you got, just much like the eye, only where you need in high uncertainty should you have the high res. Everywhere else you could just sort of use prior probability distributions, kind of like, you know, we kind of know where things are. And I think that is sort of a brilliant step forward in that. And I see this sort of technology becoming as commonplace as eyeglasses for every instrument, for everything we explore. Because it's really neat about this is that it's using a neat technique looking at probability distribution. So if you see patterns before, and you know, one analogy I used to say is like, imagine I give you 7 different smiley faces. We all know what smiley faces are, right? The icons. And I give it to you in really high res, 4,000 by 4,000. You see, it's beautiful. I go to Mars and I say, I just saw a frowny face. With that bit, with those couple bits of information, you can recreate something that's very close to what I'm actually seeing, right? Because you've got the prior distribution of you've seen it before. And I think the work you're doing, Paula and Jose and Piotr, of actually looking at that, how do you fuse those sensors? Start thinking about other sensors you can fuse, and then how do you make an iterative system so that when you have uncertainty, then go query the instrument to get a higher res one, and that becomes like an active eye. And that's the kind of thing, if you put that in Brian's hands, oh my goodness. mean, because it allows him the ability to see from afar with, with the physics that has these limitations. And that to me is just a fundamental advance in science and eyeglasses for exploration. It's awesome.
Yeah, fantastic.